Welcome back. So I've explained to you how the functional approach works in general. But yet again, there's a problem somehow with, well, this time not recursion, but loop. Somehow it always seems that recursion and loops, they're causing trouble, right? Because, well, you can imagine, right? They are really the core problem that arises, and because they can easily lead to infinite domains, right? And infinitely increasing abstractions. Um, and then you get non-termination, which is definitely something that we don't want. And so in general, if you have such a setting here, where maybe you have some initial prefix, but then here you have a procedure part F2, so that could be some basic block or a sequence of statements that is part of a loop. Then, like you saw, basically as you iterate through the loop, you can increase your summaries more and more, and this well basically never really terminates, right? And the problem is that this expression here, the symbolic expression, it keeps growing indefinitely, and there might be a chance though to make this terminate, to somehow force this to be finite, and that is if there were a way to reduce any of such expression to a finite normal form, right? And it must be a normal form, so that means whenever I have two expressions that are equivalent, they're really being merged to one and this, or they're reduced to one and the same expression, to one and the same normal form, because then you get the guarantee that if you apply this in every single iteration, that you basically will reach a fixed point, right? Because then basically you have a finite abstraction, right? There can only be a finite number of normal forms, and if you assume that, and that's really the case, then the abstraction is finite, and you're guaranteed that you cannot be extending this forever. Okay. So this only terminates if all compositions and meets can be reduced to a finite set of functions. Okay, that's the whole point. Now, we've seen that if you do this naively and you don't have this property, then you have this continuous growth, and hence you need to simplify them. And the simplification, it does ensure termination. So it's essential for that, but it also makes function application more efficient in general, right? Because if you have functions that are not expressed through any of such large terms, but they're actually being reduced to some conveniently small normal form, that also makes applying these functions more efficient, of course. But the problem is that not all flow functions can be reduced. But the question is which ones can. And that I want to explain to you next. So let's take a look at special classes of flow functions. And first I want to take a look at flow functions that are called separable. So if you take a look at a very general flow function, it generally really has this form. So it takes a number of input values, some data flow values d1 to dn, and then it computes some arbitrary function that gives you some other vector of data flow values d1 to dn. And in the very general case, there can be any kind of relationship between any of these inputs and any of these outputs. The only requirement is really that this needs to be deterministic, right? But that's it. Particularly any of these values can depend on any particular combination of these input values. For a separable flow function, that is not the case. A separable flow function is also a flow function, but it has the property that d1 only depends on the previous value of d1, and the same for d2 and up to dn. So really, every single entry in that vector, you could say, is computed or can be computed separately. And that's also where the name obviously comes from. To show you one example, you can think about live variables analysis, which determines which variables are still being used later on in the program. So this is actually a backward analysis. And if we assume that we're doing a backward analysis to this very simple program, which uses x here, and then x is defined here, so y is being used by that statement, then this is actually what a live variables analysis would compute here. At the end of the procedure, the analysis starts and nothing is live yet. But then here x is live because in the remainder of the program, in this print statement, it's being used without being redefined earlier. And then here, this statement, it redefines x, but it uses y. So that means x is now actually not live any longer because it's being redefined, but y now is. And the effect of this statement here, for instance, it can be expressed as such. So you're generating y and you're killing x, okay? When you go through this statement from the bottom to the top. And if you take a look at this flow function, it is actually separable because it's killing x no matter what. So this is not even depending on whether x was valid before. It's killing x no matter what. And here, it's generating y no matter what, right? So this is even simpler than separable, but in particular it's independent of any condition, and therefore it's also a separable function. So these separable problems, they are also known as so-called bit vector problems because their flow functions can actually be implemented as very simple bit vector operations. So you can simply basically look at one bit at a time, right, individually, and you can simply say, for instance, you know, if one bit was true previously, depending on that information or not, you'd then generate or kill a particular piece of analysis information by flipping that bit or not. And the thing is now what we are aiming for, it's somewhat related, as you will see later, but it's actually going a little bit beyond separable flow functions. So it is more expressive. So we don't assume that our flow functions are truly separable, but something a little bit like it. You will see that on the next few slides when I explain it to you. What is similar in terms of the idea is that we want to somehow divide and conquer. We want to be able to decompose flow functions. But the decomposition now, it's a little bit different from what you saw earlier. What I showed you in the beginning is that in a general flow function, the output values, they can depend in any way on the input values, right? That only needs to be a deterministic relationship. But now we assume that we can deconstruct the flow function into a number of component flow functions. And this you can always do because in the end, f is computing these output values. And like I said, they can depend in any way on the input values, but you can decompose f such that it computes each of these component output values separately, right? So we can first compute only D1 based on all these different inputs, and then we can compute only D2 and so on, right? So in the simplest case, if you wanted to define such a function f2 that computes only D2, in the simplest case, you could really take all of f and you could simply project away all the other components, right? But often there are obviously more effective implementations of these individual component flow functions. But that's the first idea, that we take our flow function f and we decompose it into these different component flow functions that compute d1 up to dn based on all these different inputs. Okay? Now the point is that in many situations, you can have component flow functions that have a special form. And if they have that special form, we can exploit it to our purpose. And that will make it also usable in this functional approach that we saw earlier. So let's assume we are now looking at one single component flow function, right? So we're just looking at F2, which is computing D2. And for now, we don't care about the other components, but for the other components, you can do the construction in the very same way. Now, like I said, D2, the value D2 down here, depends in any way on these other values D1 to Dn, right? And in the very general case, this can be an arbitrarily complex function that, I don't know, it does an arbitrarily complex computation on these values to then derive at this output value, okay? But now let's assume, and that's really now an assumption, that we can decompose F2 as follows. So we assume that we can first compute some partial effect that D1 has on D2, and that's computed by this function here. And then we do the same for all the other input components. Okay, so we now have n different microfunctions. That's actually what we call them here. Okay, n different microfunctions that all contribute to this component here. And in essence, we have n times n such functions, right? Because we have n such microfunctions that compute D2. And we also have n functions that compute D1 and so on, okay? Now the question is, if you have such functions that compute these individual effects that every single input value has on this output value, then how do you arrive at the final output value D2? And here again, we assume that we are given some meet operator or some merge operator, okay? So we assume that you can really compute this, well, in a separable way, right? So you do this one component after the other, and then you obtain the final result by simply merging over it. And so you have these n times n microfunctions or primitive entity functions, as they are sometimes also called in the literature. Okay, now this seems like an interesting construction, but how does this help us with summarization? Why is that useful? Let's take a look at what happens if you do this construction not over a single statement, but over a sequence of statements, okay? So let's assume we have some flow function f and one flow function g, and we are decomposing it in the way I just showed you, right? So over this statement here, we're basically computing the effects through these different microfunctions, and then we are applying the meet operator here to arrive at this data flow fact, at this vector here. And then we are again doing the same for a different statement with a different flow function and therefore a different set of microfunctions that gives us this vector down here. And now the thing is, we want to summarize this, right? So we want to represent what we have here using something that looks like this, right? So ideally, we would want to have a summary function that is expressed in the same way, that that takes some input vector of data flow facts that is valid at the beginning of the procedure or at the beginning of the statement sequence here. And it computes using the same method some vector of output values, right? So also here we are having some microfunctions, but now they span the entire procedure. But we can use them to compute the effects on these different output values separately, right? So for each input value separately. And we obtain the final result again by using the meet operator down here. Now, if we take a look at this, what does this here on the left-hand side represent? Well, this is basically saying we apply f, right, the flow function f, and then we are applying some meet operator. Then we are having some g functions, and we are again applying the meet operator. So conceptually, it looks a little bit like this, right? So first f, then meet, then g, then meet. What do we have on the right-hand side? Well, conceptually it's this, right? So here we also have micro functions, but as you will notice, they now combine the effects of f and g, and we only compute the mean in the end. So we have seen something like that before, right? So this is essentially doing the same, but it's merging earlier, right? It's merging more often. It's merging here, whereas on this side we are only merging down here. Other than that, it's essentially the same, right? So the question is now, when is that an exact representation of this here? When do these two equal? Well, we have seen that before, right? When does this hold? You hopefully remember it holds if and only if f and g are distributive over the merge operator, right? If they distribute over that operator. And that's exactly the essential property that you require for the functional approach. So if you want to have an instance of the functional approach that really computes precise procedure summaries in a symbolic way, right? Like I showed you, that sort of accumulates these effects of the data flow functions in summary functions, then if all of these flow functions that you're summarizing, if they distribute over the merge operator, then exactly they can be reduced. And then you can have a finite representation of them. And then you also guarantee termination. And what's important and interesting again, as I showed you earlier, if you have a distributive problem, such as here, then we already know that the MOP solution of this problem is actually computable, right? Because it computes, it's computed by the MFP solution. They are identical. So that means if you can apply the functional approach in this way, because you have a distributive problem, you not only can use the functional approach, with ease, but you even get a perfectly precise solution. So that means if you have a problem that fits into this, it's actually really nice. You can get a long way with it. Now, getting back to this example I showed you earlier, the problem was that this here, it's actually not distributive. So if you have such a statement here in constant propagation, where the output value is actually depending on two different input values. Here it's depending on x and y. Then this is exactly not separable, and it's also not distributive, because you really need to know both the values x and y in order to compute a precise output value for x. That does not work. You could turn this into a distributive instance if you were to approximate in these cases. So if you were to define a data flow function here that simply says, okay, if I do have such a right-hand side where I have two different relevant input variables, x and y, I simply abstract away from this by immediately doing a widening, right? By immediately going to top. Then it becomes a distributive problem. You could solve it in a distributive framework, but it would need to approximate in several cases, right? So this would not be precise, but it would assure termination, and it would allow you to use the functional approach. And sometimes that can be a valid choice, right? Depending on what you want to do, that can be actually preferable over using another non-distributive framework, over using the call strings approach, for instance. You might still get better efficacy in the end. So let me recap. The functional approach, it works by computing a summary for each call method. Okay. And then at each call, the call's flow function, it's really simply the summary function for that particular procedure that is being called, but it's translated to the caller side, like I showed you, through these call flow and return flow functions. Then summary functions, they are computed through incremental extensions along the control flow graph. But then we saw that we need to reduce flow functions to avoid infinite growth in the presence of loops in particular. But without loss of precision, we can always reduce compositions and means of distributive flow functions, right? So if we have that property, then you get this guarantee, and then the functional approach is applicable. So if we contrast that again with the core strings approach, then we see the following trade-offs. So the core strings approach, it's really generally applicable. That is because, well, or what I mean by this is that it applies to any static data flow analysis that can be expressed in the monotone framework, right? So you still need monotone flow functions, and you still need the ascending chain condition and so on. But then that's all you need. So there are no additional requirements. Whereas in the functional approach, you need to be able to summarize and reduce flow functions. So essentially, you need to have a distributive problem. In the call strings approach, though, you must bound the calling context strings. We saw that you need to choose a k, and I told you typically it needs to be also a small k. Interestingly, in the functional approach, if you're using these distributive flow functions, you have infinitely deep context sensitivity. So essentially you have an infinitely context sensitive problem. K is infinity. Because, well, there's no need to explicitly store calling context strings. They don't occur in any of what you saw, right? So essentially the calling context strings, they are only encoded in terms of the data flow. So we are not storing any call sites here. We're not storing any information directly on what the call string looked like when we were calling a certain procedure. The only thing that a summary is storing is information about what the data flow in the context looked like when we were entering the procedure, right? That's encoded in the summary functions, because a summary is essentially saying I'm mapping to a certain data flow value, but from a certain input data flow value. And any context that makes this input data flow value hold, to any such context, the summary can be applied. We'll see more about this in the next lectures I'll be giving. Then also we saw that you have duplicate work for different call stacks that use the same analysis information. This is exactly not the case for the functional approach, right? So here we have summaries that are being reused for all call strings that yield the same analysis information. That was the entire point of applying the functional approach in the first place. So I hope that gave you a good overview of what the functional approach looks like. In the next few lectures, we will be looking at a particular flavor of functional approach, first of all, that combines the functional approach with some elements also from the call strings approach. But then I will also be discussing frameworks called IFDS and IDE, which are particular instantiations of the functional approach for distributive flow functions. And as you will see there, distributive flow functions not only make the functional approach viable, but they actually also make for some very nice and very efficient encodings, which makes them very appealing to analyzing in particular large-scale programs. And we'll be covering these in depth. Looking forward to speaking with you then. Bye-bye.